For example, if we want to see the tutorial for the cylindrical case, we already have that case and we have the result that is stored in our processor. So we try to run in the parallel process in HPC, and if we go to our system file, if you go, so here you can get the option like how many processor you want to use. So basically the number of processor, it depends on vary, or it may vary like how much we want to use. So for my case, I just use a small number of um, processor, because while I'm trying to run it to the HPC, it is like merged in or collected into a one processor. For example, it has a processor number 4. So I want to show you how to run a case. So I'm taking a simple example. So for running a case, we need like three important folders that need to be available on a specific folder. So for example, we need like org, constant, and system file. I'm also trying to copy other folders. It might be necessary or not. So then I'm trying to create a folder name with trial. So I'm pasting all these folders. I hope. Yeah. Okay. So sometimes what we can do, we have it. I already documented the steps. So these are the documentation. So if you see case folder structure, it might have name, it have a specific folder names O, and a constant folder. In the constant folder, it have two subfolders like the polymesh, and other folders like named with like transport properties or turbulence or sedimentation properties. And the third important is the system, where you have the options of editing or modifying the control disk, every scheme, and every solution. It also have like decompose folder. So when we have all this folder, our next step is to provide this commands line. So these are the all commands line to run a processor. So the first one is the block mesh. So the block mesh is used to create a geometry. So we can use or we can create a geometry from any other software like the ANSYS or other one. But in the OpenFOAM, it also have a ability to create the structure. If it's simple, then we can use the block mesh file. So if I go to the block mesh file, yes, this one. So this is the block mesh file. So it has some vertices and how many blocks we are using and which one we are assigning it as the boundary condition. For example, like inlet, outlet, and top wall, lateral front, and lateral back. So this is typically a format of using the block mesh file for creating a simple and easy geometry. But if it's complex, so it's better used to um, create that geometry in other software like for example ANSYS, and then compile it to here. So for our case, because we are running a simple cylindrical case, so where we have a rectangular domain and we need to put an obstacle. So for the rectangular domain, we are using the block mesh file to create a rectangle, and we are subdividing into three blocks. And for cylindrical like cylindrical object, we can use also block mesh file, but for our cases we are using We already created a cylindrical object and compile it here as a STL file. I'm gonna also like show it how to do that. So for the geometry, we can use, because as we are using the block mesh dict file, so we need to provide the command line block mesh. So after providing the command line, it will create the geometry. If you see, I'm going to provide the command line. Okay. If you see that the mesh is already created, and if we go to the our constant folder, it will also created another folder where named with the poly mesh, where you can see how many boundaries and other information like how much points and cell faces are generated after having the command line block mesh. So for seeing the geometry, we are using the ParaView software for visualization. And so as we already created the geometry, our next step is to create a foam folder so we can compile it in our visualization. So for that, I'm using a name, a foam. Uh, this one is the command line. Um, I forget about just example. For, for, Okay, so the command line is like attach m.fom. Okay, fine, it's created. So now our next task is to visualization. So I'm going to the para view. So for the paraview, I need to go to the file folder and click on the open button. Here you can have the option like that, the folder you already created. So I need to select this one. So I just used a simple name aim. So it depends on you like which one you want to rename. So you can put any name, whatever you want. So I'm putting it like the OK, and you need to select the option of the button apply. So while you are applying, you can see a simple rectangular geometry is already created. So as I already mentioned, we are running a scour case where we have a rectangular segment. It in the rectangular segment, which is divided into two segments like the water and sediment. So I'm providing this rectangular certain division, like this portion would be the sediment concentration, and at the top it will have the water zone. So for that reason I created a rectangular geometry. So this is our rectangular geometry, and in the block mesh file, at the last you can see we have like some options of the boundary conditions. So those boundaries which I already created can be also be visible at the left side. If you say we already selected the internal mesh, if we undo it or unselected it, we can see we don't have anything. Right now we want to see what is our inlet. So if we select the inlet, you can see how much portion is already provided as a segment of the inlet. So this portion is the inlet. So Internal mesh, which represents our full mesh, and if you unselect it here, you can see how much only inlet is considered into a total whole domain. And if I select in the outlet portion, this one is I named as a boundary outlet, and after I applied it here, you can see. So this one is my outlet, and this one is my inlet. And if you want to see the bottom one, so I consider this one is as a bottom one. So for the reason I provided this portion is bottom, because here it will have some sand, so it will not considered as the inlet. So for this one I incorporate the lower portion from the front is also as a bottom wall or bottom segment. And if I provided some uh let me see, what is this one? I think it would be the top one. Yeah, this one is the top, which is considered as a like symmetry surface. And for the front and back, we are considered as a cyclic boundary condition. So you can see this one is considered as a front, and this one is considered as a back. So this is the whole geometry we created using our block mesh file. So yeah, yes. And if you want to see some like solid color, okay, let's see what, yeah. So here you can see certain different color to get more visualization, like which one is the inlet and which one is like our outlets. And I'm also selecting the bottom one so that we can see our whole geometry. Yeah. I didn't like select for the outlet section. So if we select the outlet section, it will also be like visible. And I think we can also get the option. So this, like if you see how many blocks we have one, two, three, four, five, and six. So there's three like boundary condition is generated in our block mesh file. If you see, it will have like all these uh, blocks. So this one is the one, two, three, four, five, and six. And at the same time we can also get the coordinates. So for my easiness I put all these coordinates names. Sometimes we can see, just one minute. No, no, I think I forget about like how to show all these coordinates to assign this. Okay. So when we have the geometry, our next step, if we see in our command line what is mentioned, it was like snappy hex mesh override. So the snappy hex mesh override that we're using to create to provide or to implement our cylindrical object. So for the cylindrical object, I use the STL file to create this cylinder. Uh, okay, I shouldn't like stop this one. I'm trying to show where my STL file is created. In the same way, I'm again opening my foam folder, foam file. So I already have this and showed how to do this one. Then I'm trying to show you like the cylindrical objects, the cylindrical obstacle that I put in our try surface folder, which is named as cylinder STL. So for cylindrical object, I use the FreeCAD software to create that obstacle and export it as a STL file. So if I apply it here you can see an obstacle of the cylinder. So this obstacle is created as a STL file. So initially, we have a rectangular solid surface. Right now, we put an obstacle in a cylindrical shape, and the cylindrical obstacle is created as a HTML file, and we want to like create here as a follow. So for that purpose, we need to like provide this step, which is a snappy hex mesh override. So I'm trying to copy this one and put the command into our terminal. So let's see what happens. Then it would be better to explain. So I already copied. If I paste it here, so it's running, it's working. I also want to show you some other thing. For running the Snappy Hex Mesh file, you need to be available some two folders in your system, that is like Snappy Hex Mesh D and Snappy Hex Mesh K epsilon. So if I open this folder, you can see the options. So we already have a surface of the we need to provide some maximum and minimum value. So this zone is like used to refine our certain domain, because we are focusing on the scar dynamics. So we try to provide some refinement around the cylindrical obstacle, and the cylindrical STL file is assigned as a geometry. We need to put the file name and name cylinder, and it also have some other refinement level, like how much refinement level you want to use. So for my cylindrical case, I used refinement level 1, and I also need to assign a location mesh which should be inside between the provided region in the searchable box. So this is my refinement zone, and I need to show a point which will be inside this zone. So I think the what so it's running. So it might take some times because of this one. So if it's a larger zone or larger box, so it might take time, take a little bit more time. And from this one we can see how much mesh or how many cell is generated. So if I again open the paraview folder to see, previously I have a solid rectangular block. Right now, I opened it in a similar way. So here you can see what is the difference between the first and the second command line. Okay, so I think right now you can see the difference between the first and second one. So previously we have a solid block, but when we are using the snappy hex mesh, so snappy hex mesh is creating a similar block or similar obstacle inside the domain. So if you see, if we try to open our cylinder, which is available in our constant folder, in the try surface, go to the try surface, open it. Yeah. So you see, we have a obstacle cylinder, and we incorporated this obstacle into our domain by using a snappy hex mesh file. So in the similar way, in our further cases like the sea hive, as it was a very complex geometry, so which is not being feasible or possible to create into through our block mesh command line. So for that purpose, we can use a snappy hex mesh to incorporate different or complex geometry into our domain. So that is the way we used our second command line. And the third one is the CPR org zero folder. So this is the command line we use to create initial time folder. That means our initial time zero folder. So before running our case, we need to provide this command line. So if you see, we have previously zero org folder, constant folder, and system folder. But while you are providing this command line, the CP is used to copy this command line with a named zero folder. Okay. Okay, I'm pasting this one here. Before pasting this, let me see. We already have three folder, right? So while you do this, you can see. Okay. Uh, folder named with zero will be created. So it means that we are copying this folder into a new folder that is named O. And here you can see all these folders are available, which is already be there in the zero RG folder. So that command line is using for creating a zero time strip, and then our next step is like to run. So it depends on like if you want to run a parallel process or serial process. So in our cases we are using the parallel process, so there might be some difference why we are using the parallel process or serial process. So I don't wanna go to explain all these details. So for my case, as I'm using a parallel process. So the parallel process, I'm using the decompose command line. So it will create some processor. So you can see the changes. So firstly, I'm running the command line decompose per. Yeah, you can see it's creating some the processor. So for this processor, using to store the results like if we want to run a 120-minute, all these results will be stored in our processor. But if you don't want to use the parallel running or and go for the serial running, so the results is not into stored in these folders. It will automatically available in the outside of these folders. So yeah, the run is completed. So as I mentioned, these options. So for the parallel processing, you need to be available a decompose per date file where you can see how many processor you want to use. So for my cases, I used a simple method, and sometimes you can use the Scotch method. For that one, you need to be available a another package of software that is the Swagford for foam. So in our cases, as we used the total number of processor is 4, so it also have some limitation based on your number of processor available to your machine. So I just run with the small numbers. Wait, oh, okay. So 4. So if we vary this name number, it also affect with our outline command. So when we are done with our decompose, and our next step is to run a simple simulation by using this command line. So we are using MPI run MP. So it depends on the how many numbers processor you used. So in my case, I used 4 processor, and the solver that we are using SetFOAM RBGAs, and as we are running a parallel, so that's why we need to parallel running, but for the serial running we just need to use this command line. That's it. And if we want to see at which time step what is the results of our simulation, what it's like, it's just a summary. So then we can use another like extension in our command line, which is t log solver. So the log solver is used to see the summary of your simulation results. That means mm, if we want to see where is my simulation is now, so it's easy to say that for 1/22, but if we want to see what is my delta T or current number or any other information, so for that we can have, if we have the log file, we can see it in our log file to check about that information. So the log file is sometimes good to see the summary of your results. And if you don't want to get that option, then you can just select this option to run your simple cases. So you need to go to this command line to run the cases. Uh, so And this device, I think it's not gonna work because the set form solver that I didn't install it here. So I'll gonna get some error because yeah, so it's not executable. Total process is failed to store because I don't have the set form package or solver. So I already run those cases in our HPC, and these are the step how to run into the HPC file, the steps, how to install it and how to work on it. So I just want to mention, uh, in my case, I showed individual, like in a specific way. I've copied this command line and run it. I copied this command line, then run again. So what you can do, you have several commands line. You can copy all those commands line and create a folder which is named with all run. And if you just apply this all run folder, you don't need to specifically individually run all the command lines. So it will do, all the command line will be run for you when you are using a simple command line. So if you see, I'm going to work on something. Okay, we are not going to run our last command line because it's not working. So I'm just commented this last line and I need to save it here. And I don't know why it's not working, the all clean command line, but it was also easy. What you have run, if you want to delete this, you can use all clean. It's not working. It's saying that permission denied. Let me check it again. Why it's not working? Then try to do it like to resolve this problem by providing this command line. Let's see, is it working or not? So, okay, then I have to, yeah, it's working. So previously we have a zero folder and processor folder, and if you go to the constant file, it has the polymesh folder, but it doesn't contain any other files. So yeah, so when you are using the clean folder, it will automatically delete it all the steps that you apply to run this case. So in the similar way, we can use the all run command line, so which will apply all those commands line to this folder and to run it. So in the similar way, so it should be all done. I think it should gonna work off. See, sometimes the permission might be denied. So yeah, I think it should gonna work. So if you go to our all run folder, let's see what are the command lines available. So it will like first go to our block mesh step. So it will create the block mesh, then it will create the snappy hex mesh, copy the zero org folder and create the decompose processor. So let's see. Yeah, you can see this is the first step, like creating the block mesh. Right now, the second step is running, which is the snappy hex mesh override. And oh, I also forget how to show the number of meshes, so I'm gonna like show it after completion of running this one. So it's running still about the snappy hex mesh. And so as it's running very fastly, you can see this option might be properly. But when it is in this step, definitely the previous step is already done. Okay. Yeah, it's already done. This is our second step. So I already said that as it's running very fast, you are not be able to like see when this step is done. So right now this is the decompose per steps, which is already started to creating some processor. If you see in the steps, yes. So it's almost done, I think. Yeah, yes, it's almost done. So sometimes we want to mention in our analysis or in our paper, like write up how many number of cells that we used in our analysis. So for this one, we need to select a command line, check mesh. This one is the check mesh command line. From here, you can see your block mesh file is okay or not, or did you use any poor mesh configuration or not. So this is the way we can check out. So that our total number of mesh is like 1.8 million. So this is our total number of mesh for this case. Yeah. So it also depends, like if you want to reduce the number of mesh, sometimes it's very like have a problem with the computational cost. So if you want to reduce the computational cost, because as we are running into the HPC, so it might reduce some time to complete the simulation. But if you want to reduce the number of mesh, there might be some two-way. One is like you need to reduce the number of cells from the block mesh file. If you see, we use 10, 12, 30. That means when we have this block, it's a rectangular block. So the x-axis is divided into 100. The y, I think this one is the z, and the z, yeah, vertical direction. So vertical direction is divided into 12, and the z direction or width direction is divided into 30. So if you reduce these numbers, then you can get less number of mesh. And other way, as we are using the snappy hex mesh file, so we created a searchable box. So there might be another option. If you select small searchable box, like a smaller region, you can reduce or modify this number of coordinates. So yeah, I think if you see, it started from -2, 1, 2, 3, 8. So for example, so I have a refined length with 0.59 length direction, and in the width direction it was like 0.2. So the length is 0.2 and width is, so the length is 0.59 and width is 0.2 meter directional. So if I reduce this, it might like reduce the number of meshes. And yeah, I can show you the refinement level where it is. Now, just 1 minute. You can see we need to open our paraview folder to see the refinement. I'm going to my previous command line. I want to show something over here. So firstly, let's start with our meshes. So after having done with the snappy hex mesh file, you can see how many mesh that you used in your simulation. So this is the solid mesh. If you go to the wireframe, where you can see how much refinement is here. Did you see? Yeah. It's like the number of division or number of mesh which is showing as a wireframe. So this is the surface with edges. So where you can see how many like refinement is applied to our mesh. So in our snappy mesh file, we have some refinement, but at the outside, it's not be like possible to visualize. So that's why I'm taking a slice to see where is my refinement. So if I take a vertical slice, Z direction, so where you can see where is my refinement is available. Yeah. Did you see? So this is the block. We have a refinement level over here. And if you I go to y directional, I need to put it like little bit lower so that we can see how much refinement is the Z direction. Yeah. See, this is the vertical Z direction refinement. So that's about the refinement. Now I want to show you like when we're using a zero RG folder and decompose folder, it's created a results for our initial time steps. So previously we don't have any sand concentration. So when we have the results of the zero time step, for this one I need to select the skip time zero to see the results of our first time step, which has nothing is movable or nothing is changing. And we need to select the case type decompose case because we are using a parallel running. So we need to apply this one. So for this one, you can see we have a 0 and 1. This is the time step showing. So here we can see we have a like alpha, which is the sediment concentration. If you apply it here, where you can see. So this is the red revision represents our sand, and the blue is the water, and I put obstacle here. So previously, while I'm explaining about the boundary conditions, so if you see, as we have like sand layer here, so this will not considered as an inlet, because if we consider it as an inlet, the sand will move away, but we don't want to do that. So that's why we consider this as a fixed. So I incorporate it with our wall boundary conditions. And but at the outlet, we consider the full one is our outlet because it can move anywhere, or when the water is flowing, some sediment will deposit at the downstream from the upstream. So this is the results of our initial case. And while we start running, we can see how much deposition or how much sand is moving from upstream to downstream. Yes, so that's all about the initial steps to run a case in the OpenFOAM and in how to see the results in the ParaView. So in our next steps, I'm gonna explain how to visualize those results when we are done with our simulation or our analysis, like how we can extract the results from the ParaView and visualize it, and how we can change or modify anything if we want to do it in the ParaView.